Today I'm going to have a look at the distributions and hypothesis testing that is required for OCR Further Maths. Before I get into the details, let's have a quick look at what the specification says about hypothesis testing. You should be able to conduct hypothesis tests using binomial distributions to test the probability, normal distributions to test the mean of a sample from that distribution, and to test the correlation coefficients between two variables. And at the end, I will do a short example of each question type. Let us start by quickly looking over the distributions that we should be testing. Firstly, the binomial distribution. The binomial distribution is a distribution that models a random variable that has a fixed number of trials, independent results from each trial, constant probability, and the same outcomes each time. Normally the question will specify which distribution you should use, but if it doesn't, think about whether you could define the variable with a yes or no question, like, was something defective or not? Did they hit the ball or not? The notation for binomial distribution is x is modeled by the binomial distribution with n trials and a probability of p. It is important to remember this notation, as there usually is a mark for the correct use in questions. One more thing to know is that there is a significant difference between less than or less than and equals to in the binomial distribution. This means that if you're looking for less than a number, you need to use binomial CD of the number below it, because it will always give you less than or equal to as an answer. When testing the binomial distribution, you will just test the likelihood that a single result came from an assumed population parameter. The normal distribution is a distribution that models a continuous variable, such as the length of time a lamp shines or the height of people. Unlike the binomial distribution, there are an infinite number of data points along the line. This is important because there is no difference between less than and less than or equal to in this distribution. The normal distribution notation is x is modeled by the normal distribution with mean mu and variance sigma squared. Make sure you always root the sigma squared value, because you will always be calculating with regards to the standard deviation, which is sigma. When testing the normal distribution, you will test the likelihood that a sample, size n, came from a normal distribution. This works because the mean of all possible samples will produce another normal distribution, modeled by x, size n, is modeled by the normal distribution mu, sigma squared over n. Converting the variance is an important step, and you should lay this out clearly in your working. An even quicker recap on the correlation coefficient. The R value simply models how closely two variables are related, one being perfectly positive and -1 being perfectly negative. The main terms we need to know for hypothesis testing are what a population parameter is, what the null and alternative hypotheses are, what the p-value is, what the significance level is, how to use critical values, and one- and two-tailed tests. A hypothesis test is a procedure to test a certain population parameter, called a test statistic. We set up two hypotheses, one based on what we assume is true, called H0, or the null hypothesis, and what we think might have changed based on the observed data, called H1, or the alternative hypothesis. A population parameter is simply a number that describes the data you take your distribution from. This becomes a test statistic once you use it in a hypothesis test. In the case of binomial distributions, the value you will be testing is p, and in the case of normal distributions, you are testing the mean. Finding our two hypotheses is probably the most important step in a hypothesis test. As I said earlier, H0 is what you assume is true from the population. This will usually be the test statistic that they give you in the question. H0 is always an equality statement. If you've gone wrong if your H0 has any sort of inequality in it, and H1 is the alternative hypothesis that we think might be true. H1 will always be an inequality based on the value given in H0. For example, if H0 is that p equals 0.2, H1 will be that p is not equal to 0.2, is greater than 0.2, or is less than 0.2. And in order to identify which one of these it is, we need to look for the keywords in the question. If the statistic has increased, there will be a greater than. Decreased will be a less than, and if it just says changed, it will be not equals to, and we need to perform a two-tailed test. I'll get onto this later. P-values. Finding the p-value is the real meat of any hypothesis test question, and once you know what to do, it is as simple as putting the values in the calculator. The p-value is simply the probability of the observed value or more extreme occurring based on the distribution. Graphically, you are testing the entire shaded tail here for the probability of that tail. You do this by putting into your calculator the observed test statistic along with the other population parameters. For example, if it is assumed that p equals 0.4, but out of 20 tests we get 4 results, and we test the chance of getting 4 or lower. This probability is the p-value. For a normal distribution, there is an extra step. If the population mean is 100 and variance 4, and the sample of 3 has a mean of 120, we must first divide the variance by the size of the sample, and then test the probability that a value of 120 or greater occurs. Now let's talk about the significance level. The significance level is another important number that you'll be given in the question. The significance level will be given as a percentage, but treat it as a decimal probability, i.e. 10% equals 0.1. This is the minimum value of the p-value that you'll tolerate before you can say, this is so unlikely that this observed data came from the population that we can suggest that the population statistics are different. An alternative to using the p-value that you can use for the normal distribution is the critical value method. This is simply using the inverse normal function to see at what value the probability of a result would be lower than that of the significance level. You can then compare your observed data to your critical values and make a conclusion based on which side of the value that they lie. This is a good chance to talk about two-tailed tests and one-tailed tests. So far, everything I've said has been in reference only to one-tailed tests. It mostly holds true for two-tailed tests too. However, two-tailed tests are the ones where your H1 involves a not equals to. Two-tailed because you have to test the upper tail and the lower tail. You will most often be using the critical value method for this. However, the one point to bear in mind is that you should compare your p-value or find your critical values using half the significance level, because you're effectively splitting it up into upper and lower. And you also have to find two critical values, the upper and lower critical value. This is a really important thing to remember. Alright, let's start by doing some examples. So we'll start with the binomial distribution hypothesis test questions. So this one is, Bob believes that a coin shows more heads than tails. In a sample of 200 flips, the coin showed heads 116 times. Does this support Bob's hypothesis at a 5% significance level? So first we need to start by identifying our H0 and H1. This is key to every single hypothesis test question. So H0 is that P equals 0.5, because we're assuming it's a fair coin to start with. However, H1 is what we think might be true, so that P is greater than 0.5. We think it shows heads more times than half, and so P is the probability that it shows a head. So X is binomially distributed with 200 trials and a probability of 0.5. We then need to look at the significance level. The significance level is 0.055%. So calculating the p-value, p is what's the probability that x is greater than 116. This is the same as what 1 minus p probability that x is less than 115. So that is 1 minus 0.985. Otherwise known as 0.0141. And then we compare that to our significance level, which is obviously it's less than the significance level, so we have sufficient evidence to reject H0 and that the data suggests the coin is unfair and shows heads more often than not. So let's have a look at this question. It is believed that testosterone levels in blood are normally distributed with a mean of 24 nanomoles per litre and a standard distribution of 6. Following the race, a sprinter gives 2 samples with an average of 34 nanomoles per litre. At a 1% significance level, is there enough evidence to suggest that the sprinter has more testosterone level than the mean? So we start by identifying H0 and H1 as always. So H0 is our population statistic, which is mu equals 24. Our H1 in this case is we want to look at is it greater than the mean, so therefore mu is greater than 24 for H1. We then write down that X is equal to the level of blood and testosterone in blood. Clearly identifying that variable is important to get all the marks in these questions. Then write down the model. X is normally distributed with a mean of 24 and a variance of 36. Our X bar 2 is equal to the mean levels of testosterone in that sample of 2. Again, clearly identifying this will get you all the marks in these questions. X bar 2 is normally distributed by a mean of 24 and a variance of 36 over 2. We then work out what the p-value is for this. So p, what is the probability of X bar 2 being greater than or equal to 34 in this case? It is 0.00921. We then compare this to our significance level. See that it is less than our significance level. Therefore, the chances of this happening are less than the boundaries we set up, and therefore we have significant evidence to reject H0 and suggest that his testosterone level is above the mean. So let's finish up some correlation coefficient questions. These are a bit different to regular questions, as you don't have to calculate a p-value or a critical value. You just have to identify your number of trials and your significance level, and you look up the critical value in the table you have been given. So let's have a look at this question. The correlation coefficient between the mass and height of students in a sample of 6 students is 0.85. Test at the 5% significance level where the height and mass of students from this school are positively correlated. So with the correlation coefficient question, the H0 will always be that rho, your PMCC of this sample, is 0, because there's nothing to suggest that there is any correlation in the general population, so therefore rho is always 0. H1, rho is greater than 0, because we're looking for a positive correlation in this sample. So rho equals the PMCC of the students, and R equals the PMCC of this particular sample. So R equals 0.85, and the significance level is 5%. And we have 6 trials. So therefore we look up in the tables provided what the critical values are. In this case, the critical values are 0.729. And then we see that our R value is greater than the critical value number, and therefore we can conclude that there is sufficient evidence at the 5% significance level to suggest that this population has a positive correlation between weight and height.